Welcome to DAR Tutors. This video provides online and home tuition. In this lesson, we will systematically cover key concepts in acids and bases, directly aligned with the IB Chemistry higher level curriculum. By the end of this video, you will be able to, first, differentiate between strong and weak acids and bases. Second, identify conjugate acid-base pairs. Third, accurately calculate pH and pOH values using the ion product constant of water. And finally, analyze the effect of temperature on the pH of water. Let's begin. Our first topic is the distinction between strong and weak acids. This is a fundamental concept in acid-base chemistry. A strong acid is defined as one that completely ionizes or dissociates when dissolved in water. This means that virtually every molecule of the acid releases its hydrogen ion. Because of this complete dissociation, the concentration of hydrogen ions, or hydronium ions, in the solution is essentially equal to the initial concentration of the acid. For a monoprotic acid which donates 1 proton per molecule, like HA, the reaction goes to completion. At equilibrium, there are virtually no HA molecules left. The solution contains only hydronium ions and the conjugate base anion. 1 mole of a strong acid produces 1 mole of protons or hydronium ions. Common strong acids you must know are hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, chloric 7 acid, and the first ionization of sulfuric acid. Weak acids, on the other hand, are only partially ionized in water. This means an equilibrium is established where most of the acid molecules remain undissociated. Only a small percentage, often less than 1%, react to form ions. For a weak acid HA, the equilibrium lies on the left-hand side, favoring the undissociated acid molecule. At equilibrium, the solution contains a mixture of the original acid molecules, hydronium ions, and the conjugate base anion. The concentration of hydronium ions is significantly lower than the initial acid concentration. A crucial distinction to make is the difference between acid strength and concentration. This is a common source of confusion. Concentration is simply the amount of solute per unit volume, usually measured in molarity, mol dm3. A concentrated solution has a high molarity, while a dilute solution has a low molarity. An acid's strength, however, refers to its extent of ionization. Therefore, you can have a concentrated solution of a weak acid and a dilute solution of a strong acid. For example, a 10 mol DM3 ethanoic acid solution is concentrated but weak, while a 0.01 mol DM3 hydrochloric acid solution is dilute but strong. Let's work through an IB-style example to solidify this concept. Suppose we want to compare two solutions. Solution A is a 2.0 mol DM3 solution of methanoic acid, HCOOH. Solution B is a 0.5 mol DM3 solution of hydrochloric acid, HC. Let's first address which solution is more concentrated. This is a question about molarity. The methanoic acid solution, with 200 mol DM3, is clearly more concentrated than the hydrochloric acid solution, which has 0.5 mol DM3. Now, let's identify which is the strong acid. This is about the extent of ionization. From our discussion, hydrochloric acid is one of the common strong acids, meaning it dissociates completely. Methanoic acid is an organic acid, which are typically weak, so it only partially dissociates. Therefore, hydrochloric acid is the strong acid. Finally, let's determine which solution has the higher concentration of hydrogen ions, H+. This determines its pH. For the strong acid, HCl, its dissociation is complete. A 0.50 mol DM3 HCl solution will yield 0.50 mol DM3 of H+ ions. For the weak acid, HCOOH, even though its initial concentration is much higher at 2 mol DM3, it only ionizes to a small extent, typically less than 1%. This means its H+ will be much smaller than its initial concentration. Comparing the two, 0.52 is much greater than any value less than 0.02. So, solution B, the dilute strong acid, has a higher concentration of hydrogen ions than solution A, the concentrated weak acid. This example clearly demonstrates that concentration and strength are not interchangeable concepts. Always consider both. The same principles apply to bases. Let's look at strong and weak bases. A strong base undergoes almost 100% ionization in aqueous solution. This produces a high concentration of hydroxide ions, OH. The hydroxide ions are released from the base molecules or formed through reaction with water. Because of this high concentration of OH ions, strong base solutions have high pH values and high electrical conductivities. Common strong bases are the hydroxides of group 1 and group 2 metals, such as sodium hydroxide, potassium hydroxide, and barium hydroxide. Weak bases are molecular compounds that react with water to a small extent to produce hydroxide ions. Unlike strong bases that release OH directly, weak bases accept a proton from water, forming hydroxide ions in the process. This process establishes an equilibrium that lies predominantly on the left. The result is a relatively low concentration of hydroxide ions compared to the initial concentration of the base. Weak bases have pH values above 7, but generally below 12, and they exhibit low electrical conductivity due to the small number of ions. Aqueous ammonia NH3 is the most common example of a weak base, along with organic amines. The distinction between strong and weak bases is just as important as for acids. Remember that strong bases lead to high concentrations of hydroxide ions and thus high pH values. Next, let's explore the concept of conjugate acid-base pairs. According to the Bronsted-Lowry theory, an acid is a proton donor and a base is a proton acceptor. All acid-base reactions are proton transfer reactions. A conjugate acid-base pair consists of two chemical species that differ by the loss or gain of a single proton. When an acid donates a proton, the species remaining is its conjugate base. When a base accepts a proton, it forms its conjugate acid. Every Bronsted-Lowry reaction involves two conjugate acid-base pairs. Consider the dissociation of a general acid HA in water. Here, HA acts as an acid by donating a proton to 2-. The resulting species, AEISILAR, is the conjugate base of HA. Similarly, 2-O acts as a base by accepting a proton. The resulting species, OC3-O plus $, is the conjugate acid of H2-O. So HA and AZ form one conjugate pair, and H2-O and a 3-O plus $ form the other. The Bronsted-Lowry definition also explains amphiproduct species, which can act as both acids and bases. A classic example is water itself. In the reaction with HCl, water is a base. But in a reaction with ammonia, water acts as an acid, donating a proton to NH+3 to form OH+. Species like water and the hydrogen sulfide ion, HSO+3 that can both donate and accept protons are called amphiprotic. Let's work through some examples to practice identifying these pairs. First, consider the reaction of carbonate with water. Carbonate, CO32, is the base, accepting a proton from water. This forms its conjugate acid, the hydrogen carbonate ion, HCO3. Water, H2O, acts as the acid, donating a proton. The resulting hydroxide ion, OH, is its conjugate base. Next, the nitrating mixture reaction, HNO3 plus H2SO4. Sulfuric acid is a stronger acid than nitric acid, so H2SO4 acts as the acid, donating a proton. This makes HSO4 its conjugate base. Nitric acid acts as the base, accepting the proton to form the nitronium ion, H2NO3+, which is its conjugate acid. In a strong acid, its conjugate base is a very weak base. A key relationship exists between the strengths of an acid and its conjugate base. A strong acid, because it gives up its protons so readily, must have a conjugate base that is very weak and has a low affinity for protons. Conversely, a weak acid, which holds onto its proton, will have a conjugate base that is relatively strong and readily accepts protons. This relationship is reciprocal. A strong acid has a very weak conjugate base, and a weak acid has a relatively strong conjugate base. You can see this illustrated in this table. As the acid strength increases up the left column, the conjugate base strength decreases down the right column. For example, the strong acid HCl has the very weak conjugate base ClCe, while the weak acid H2O has the strong conjugate base OHE. Understanding this inverse relationship is critical for predicting the direction of proton transfer in acid-base reactions. We have now reached the 10-minute mark. If you are finding this explanation helpful and wish to deepen your understanding, DAR Tutors offers expert tuition in IB, A-Level, and IGCSE curricula. Please contact us for personalized support tailored to your academic needs. Let's continue with our lesson, moving on to the pH and pOH scales. The pH scale provides a convenient way to express the acidity or alkalinity of a solution. The symbol P in pH stands for the negative base 10 logarithm. So pH is the negative logarithm of the hydrogen ion concentration, measured in moles per cubic decimeter. Similarly, the pOH scale is used to express alkalinity. pOH is the negative logarithm of the hydroxide ion concentration. This logarithmic scale compresses a very wide range of hydrogen ion concentrations into a more manageable set of numbers. A crucial feature of the pH scale is that each step of one pH unit corresponds to a factor of 10 change in hydrogen ion concentration. For example, a solution with pH 3 is 10 times more acidic than a solution with pH 4, and 100 times more acidic than a solution with pH 5. Let's work through a quick example. If a solution has a hydrogen ion concentration of 1.0 times 10 to the power of negative 3 moles per cubic decimeter, its pH is calculated as the negative log of that concentration, which gives us a pH of 3. This indicates an acidic solution. Remember the key takeaway. A lower pH value indicates a higher hydrogen ion concentration, and therefore a more acidic solution. The relationship is inverse. The pH and pOH scales are interconnected through the ion product constant of water. Water molecules themselves can ionize to a very small extent, producing both hydrogen and hydroxide ions. The equilibrium constant for this process is called the ion product constant, Kw. Kw is defined as the product of the hydrogen ion and hydroxide ion concentrations. This constant is critical in acid-base calculations. Note that its value depends on temperature. However, under standard conditions, at 298 Kelvin or 25 degrees Celsius, the value of Kw is 1 times 10 to the power of negative 14. The constant Kw means that in any aqueous solution, the product of the hydrogen and hydroxide concentrations is fixed. If the hydrogen concentration increases, the hydroxide concentration must decrease, and vice versa. Now let's derive the relationship between pH, pOH, and pKwW. We start with the Kw expression. If we take the negative logarithm of both sides, we get negative log Kw equals negative log of the product of the concentrations. Using the properties of logarithms, the log of a product is the sum of the logs. So this becomes negative log H plus negative log OH, which we recognize as pH plus pOH. The left side, negative log Kw, is defined as pKw. Therefore, pKw equals pH plus pOH. At 25 degrees Celsius, Kw is 10 to the negative 14, so pKw is 14. This gives us the fundamental relationship that pH plus pOH equals 14. This equation allows you to calculate the pH of a solution if you know the pOH, and vice versa. It is a cornerstone of acid-base calculations. Let's apply these concepts in an IB-style calculation. The problem asks for the pH of a 0.0200 mol DM3 aqueous sodium hydroxide solution at 298 Kelvin. The first step is to identify the type of base. Sodium hydroxide, NaOH, is a strong base, meaning it dissociates completely in water. So a 0.0200 molar NaOH solution will produce 0.0200 molar Na plus ions and 0.0200 molar OH ions. Therefore, the hydroxide ion concentration, OH, is equal to the initial concentration of the strong base. Now we can use this to find the pH. We have two methods. Method 1 involves using Kw. We can find the hydrogen ion concentration, H+, by dividing Kw by OH. This gives us 500 times 10 to the negative 13. We then plug this H+ value into the pH formula, negative log of 500 times 10 to the negative 13. The result is a pH of 1230. Alternatively, we can use the pH plus pOH equals 14 relationship. First, we calculate pOH from OH. Negative log of 0.0200 gives us a pOH of 1.7. Then, we subtract this pOH from 14 to find the pH. 14 minus 1.70 gives us 1230. As expected, both methods yield the same pH, which is characteristic of a strong base solution. A very important HL concept is the effect of temperature on the pH of water. The ionization of water is an endothermic process. This is because energy is required to break the covalent OH bonds in water molecules to form the separated H+ and OH ions. Since the forward reaction, the ionization of water, is endothermic, increasing the temperature will shift the position of equilibrium to the right, according to Le Chatelier's principle. This means that at higher temperatures, more H3O+ and OH ions are formed. This increase in concentration of both ions increases the value of the ion product constant, kWw. For example, Kw is 1.10 to 14 at 25 degrees, but it rises to 9.5 at 10 to 14 at 60 degrees and 5.5 at 10 to 13 at 100 degrees. Despite these changes, a common mistake is to think that pure water is no longer neutral at higher temperatures. This is incorrect. Pure water is always chemically neutral because the concentrations of H3O+ and OH ions are always equal regardless of temperature. Since Kw increases with temperature, the concentration of H3O+, which is the square root of Kw, also increases. Because pH is the negative log of this concentration, an increase in H3O+ leads to a decrease in pH. Therefore, the pH of pure water decreases as temperature increases. For instance, at 25 degrees, pure water has a pH of 7. At 60 degrees, its pH is 6.5. This doesn't mean it's acidic, it just means the scale has shifted, and 6.5 is the new neutral point at that higher temperature. Let's work through an IB-style question on this topic. The question presents the graph of Kw versus temperature and asks what can be deduced from it. Let's analyze each option. Option A is incorrect. As we just discussed, the concentrations of hydrogen and hydroxide ions are always equal in pure water, regardless of the temperature. This is the definition of a neutral solution. Option B states the equilibrium lies furthest to the right at 0 degrees. Furthest to the right means the largest Kw value or the greatest extent of dissociation. Looking at the graph, Kw is lowest at 0 degrees and increases with temperature. So, the equilibrium lies furthest to the left at 0 degrees, not the right. This option is incorrect. Option C claims the forward reaction is exothermic. An exothermic reaction releases heat. According to Le Chatelier's principle, if a reaction is exothermic, increasing the temperature would shift the equilibrium to the left, decreasing Kw. However, the graph clearly shows Kw increasing with temperature, so the forward reaction must be endothermic. This option is incorrect. Finally, let's look at option D. The graph shows that Kw increases with temperature. Since pure water is neutral, Kw equals the square of the hydrogen ion concentration, H2. An increasing Kw means an increasing H+. Because pH is the negative log of H+, an increase in H+ leads to a decrease in pH. Therefore, the correct answer is D. The pH of water decreases as temperature increases. To conclude this topic, let's work through two more comprehensive IB-style practice questions that combine several concepts. Question 1 asks for the pH of a 0.100 mol DM3 solution of hydrocyanic acid, HCN, given its Ka value. Since HCN is a weak acid, it will establish an equilibrium. We'll use an IC table, initial change equilibrium, to solve this. The dissociation reaction is HCN reacting with water to form H3O+ and Cn. Initial concentrations are 0.100 for HCN and essentially 0 for the products. The change is a decrease of X for HCN and an increase of X for H3O+ and Cn. At equilibrium, the concentrations are 0.100 minus X, X, and X. Now we write the expression for the acid dissociation constant Ka and substitute the equilibrium concentrations. Since Ka is very small, we can make an approximation. 0.100 minus X is approximately 0.100. This simplifies the calculation. We find X, which represents the hydrogen ion concentration, to be 7.87 times 10 to the negative 6. Finally, we calculate the pH by taking the negative log of X. The pH of the solution is 5.110. A value well above 2 for a 0.1 m solution confirms it is a weak acid. as a strong acid would have a pH of 1. Here is our second practice question, involving a mixture. The problem asks for the pH of a mixture formed by adding 25.0 cm3 of 0.100 ml HCl to 15.0 cm3 of 0.100 m NaOH. This is an acid-base neutralization reaction. The first step is to determine the moles of each reactant. The moles of HCl are found by multiplying its volume in DM3 by its concentration, which gives 0.02500 moles. The moles of NaOH are 0.01500 moles. Next, we need to consider the reaction. HCl is a strong acid and NaOH is a strong base. They react in a 1-to-1 molar ratio. Since we have more moles of acid than base, the base is the limiting reactant and will be completely consumed. We subtract the moles of NaOH from the moles of HCl to find the excess moles of acid, which is 0.0001000 moles. Now we calculate the concentration of this excess HCl. Remember that the volume of the solution has increased. The total volume is 2,500 plus 1,500, which is $4,000 CME3. Converting this to DM3 and dividing our excess moles by it gives a new concentration of 0.0500 mole DM3 for the acid. Finally, we calculate the pH by taking the negative logarithm of this concentration. The pH of the resulting solution is 1.602, which is acidic, as expected from an excess of strong acid. Now, let's work through our third practice problem. Question 3 asks us to find the pH of a 0.001 mol DM3 solution of barium hydroxide, Ba or OH2. We can assume Kw is 1.0 times 10 to the negative 14. First, we must recognize that barium hydroxide is a strong base. However, it's different from sodium hydroxide because it's a diprotic base, meaning it releases 2 hydroxide ions per molecule. This is crucial. The dissociation equation for BaOH2 shows that 1 mole of barium hydroxide produces 2 moles of hydroxide ions. This means the hydroxide ion concentration is twice the initial concentration of the base. So the OH is 2 times 0.010, which equals 0.020 mole DM3. Now we have the hydroxide concentration, and we can proceed to find the pH. Let's use the POH method again, as it is often more direct for bases. First, calculate POH. Negative log of 0.020 gives us a POH of 0.78. Next, use the relationship pH plus POH equals 14. Subtracting 1/7 from 14 gives us a final pH of 1230. This question highlights the importance of correctly identifying the stoichiometry of dissociation for polyprotic acids and bases. A common mistake would be to assume OH is the same as the base concentration, leading to an incorrect answer. Our fourth practice problem combines mass, volume, and pH calculations. Question 4 asks us to find the pH of a solution made by dissolving 3.646 grams of hydrogen chloride, or HCl, in enough water to make a 250 cubic centimeter solution. We are given mass and volume, but need concentration. The path to concentration is through moles. First, calculate the moles of HCl. Moles equals mass divided by molar mass. The molar mass of HCl is 36.46 grams per mole. Dividing the given mass by this molar mass gives 0.1000 moles of HCl. Next, we calculate the molarity. Molarity equals moles divided by volume in DM3. The volume of 250 cm3 is 0.25 dm3. Dividing 0.1000 moles by 0.250 cd in DM3 gives a concentration of 0.4000 mole DM3. Now we can determine the concentration of hydrogen ions. Since HCl is a strong monoprotic acid, it dissociates completely and yields 1 H+ ion per HCl molecule. Therefore, the hydrogen ion concentration, H+, is equal to the molarity of the acid, which is 0.4000 mole DM3. Finally, we calculate the pH by taking the negative logarithm of the hydrogen ion concentration. Negative log of 0.4000 gives us a pH of 0.398. This value, which is less than 1, confirms that we have a concentrated strong acid solution. This question requires a careful step-by-step conversion from mass and volume to concentration before calculating the pH. Here is our fifth and final practice problem, which brings together the concepts of KHU, pH, and temperature. Question 5 asks us to determine if a solution with a hydrogen ion concentration of 1.0 times 10 to the negative 7 is acidic, basic, or neutral. It then introduces a twist. If the solution is at 60 degrees Celsius, where Kw is 9.55 times 10 to the negative 14, is it still neutral, and what is its pH? Let's tackle the first part. Is the solution with a hydrogen ion concentration of 1.0 times 10 to the negative 7 acidic, basic, or neutral? The pH of the solution is the negative log of its hydrogen ion concentration, which gives a pH of 7. At 25 degrees Celsius, a pH of 7 corresponds to a neutral solution. Now for the more challenging part. The solution is at 60 degrees Celsius, where Kw is 9.55 times 10 to the negative 14. First, is the solution still neutral? The definition of a neutral solution is that the hydrogen ion concentration equals the hydroxide ion concentration. We are told the hydrogen ion concentration is 1.0 times 10 to the negative 7. We can calculate the hydroxide ion concentration using the new Kw value. OH equals Kw divided by H+, which gives 9.55 times 10 to the negative 8. Now we compare the concentrations. H plus is 1.0 times 10 to the negative 7, while OH is 9.55 times 10 to the negative 8. The hydrogen ion concentration is greater than the hydroxide ion concentration. Therefore, the solution is no longer neutral, it is acidic. Finally, we calculate its pH. The pH is the negative log of its hydrogen ion concentration, 1.0 times 10 to the negative 7. The pH is 7.0. This is the pH of an acidic solution at 60 degrees C, because at this temperature, the neutral point is lower than 7. This problem illustrates that pH 7 does not always mean neutrality. It is neutral only at 25 degrees. Neutrality is defined by the equality of H plus and OH, which is determined by Kw at a given temperature. We have now covered several key topics in acid-base chemistry. Let's briefly recap. First, we distinguished between strong acids and bases, which ionize completely, and weak acids and bases, which establish an equilibrium with only partial ionization. We established that strength and concentration are distinct concepts. Second, we defined conjugate acid-base pairs as species that differ by a single proton, and learned that a strong acid has a weak conjugate base, and vice versa. Third, we used the pH and pOH scales to quantify acidity and alkalinity, connecting them via the ion product constant of water, Kw, and the relationship pH plus pOH equals pKww. Fourth, we analyzed the effect of temperature on the pH of water. We learned that the ionization of water is endothermic, so increasing temperature increases Kdu and decreases the pH of pure water, even though it remains chemically neutral. Mastery of these concepts is essential for success in HL chemistry. If you need further assistance, remember to contact DAR Tutors for expert tuition. Thank you for watching.